So let's talk a bit more about graphene. Now, graphite is loads of hexagon sheets, one on top of the other. If you remove one of those hexagon sheets, you get a single layer of graphite, which is called graphene. And in principle, it's basically hexagons surrounded by hexagons, surrounded by hexagons. But of course, there's always the edge where the bonding isn't really satisfied. So if we take, for example, the one hexagon ring, you can imagine putting a hydrogen on the end of each of the atoms, and you end up with C6H6, which is benzene. And of course, as they get bigger, the sheets, you're going to have proportionally less and less hydrogen. But in principle, every graphene sheet is probably one of these hydrocarbons. It's called a polyaromatic hydrocarbon, a PAH. Just to remind you how small these things are, if you put 3 million graphene sheets one on top of the other, it would only produce a crystal of graphite 1 millimeter thick. So how do we make a graphene sheet? Well, one way is to take a pencil, which is obviously graphite, and actually draw with it. Because as you draw with a piece of pencil, fragments of graphite are coming off. And some of them will be single layer pieces of graphite. In other words, graphene sheets. And I can show that a very simple experiment that you can do. If you get a battery and you wire it up to a little LED, and on here I've got 2 metal contacts. And if I get a bit of metal, I've got a coin here, and I put that across here, it completes the circuit, and you can see that the LED lights. And that's because the coin's conducting, of course. Well, graphite is a very good conductor as well. So if I take the pencil and just go across it with the pencil here, I'm building up layers of graphite sheets, and you can see that the LED lights. And so if I take a rubber, for example, I can rub out some of these graphite sheets. Or I can use a bit of tape. Using the sticky side of the tape, I can remove lots of these layers, and you can see that the LED brightness goes down. And if I was very clever, and probably very lucky, I could probably get it so that there was just a few graphene sheets, and I could actually measure the electrical properties this way. And it sounds very primitive, and it is very primitive, but the actual researchers in the field didn't do anything that more complicated. What they did was they got a crystal of graphite, I've got one here, and with a bit of tape, you put that on the crystal, and actually you do this a few times to remove the impurities. There might be hydrogen and water and all sorts of stuff on the surface of the graphite. But once you've done that and you've cleaned it up, you take a fresh piece, put it on the crystal and pull it out. And actually what you've got is fragments of graphite picked up by the tape. Now if I bend this over, what we can do is we can then capture the graphite on both sides. And as we pull it back again, we can separate out these fragments of graphite and split them in half. And if we keep on doing that with these fragments, using the sticky tape, we can actually halve and halve and halve and halve these graphite fragments. And eventually you can make single layer pieces of graphite. In other words, you can make graphene sheets by nothing other than a piece of tape and a bit of pencil, basically. A better way of doing it is actually to get a piece of silicon, which is very, very flat, and draw the graphite across it, just like when you draw with a pencil. And sheets will come off onto the silicon. And with an optical microscope, it turns out that the multi-layer sheets, the pieces of graphite, look different from the single-layer sheets. And so just by inspecting it with an optical microscope, you can actually see the single-layer graphene layers with your eye. And then you can obviously separate them out and start doing measurements. So it's incredibly simple to make a graphene sheet. So why is graphene so interesting? Why did it win a Nobel Prize in physics? Well, it turns out that it really is a two-dimensional material. Most things in nature are three-dimensional. And because it's two dimensions, it affects the properties of this material in ways that we're only just beginning to try and understand. For example, the electricity flows through the graphene sheet much faster than in any other material. So it's got the best electrical conductivity of any material in the world. So that's the first thing. Secondly, we can in principle make them smaller and smaller because they're perfectly crystalline. All the atoms are packed together in a regular array. We can make very, very small devices out of this. Because they're small, the electricity passes across them quickly, and because the electricity goes so quickly anyway, we're going to be able to make super fast computers or transistors with this stuff, which probably take very little power. Now normally, the physics that describes solids is a thing called quantum physics, And there's all sorts of weird predictions that quantum physics has. You can even have things called tunneling, particles tunneling through other particles. Because the electrons travel so fast in this material, we have to use a thing called relativistic quantum mechanics, or quantum electrodynamics, and that's an even weirder world than quantum mechanics. The particles, the electricity flowing through the material, are called Dirac particles, and antiparticles and particles can form spontaneously, and as a result there's a whole load of amazing predictions for this very simple, humble graphite sheet, which is promising amazing new things for the future. It really is an exciting material.